Okay, we'll start the lesson. Last Monday, on Monday, we briefly introduced unsupervised learning and clustering. What's the difference between unsupervised learning and clustering? If it has a target variable, for example, these are almost the same kind of data. If it has the same data set, if it has a target variable, okay, we know how to classify them. We classify them into obesity or not obesity. Then this is a supervised learning classification. However, if we don't know how to classify them, you're given the data of a bunch of cases, and then you don't know if they want to classify, hey, just people with people tall and short, or people with obesity or not. Then it's an unsupervised learning. So why do we need to do the clustering, do the unsupervised learning, so we can treat the different group of people differently? For example, if it's people with obesity or not, later we find out, hey, they are grouped better by the weight. They can be classified into one cluster, people with a high with a larger weight or overweight, and then the other group with normal weight. Okay, we can treat them differently with different size of clothes or different treatment method. Or if it's customers, then after you put them into groups, they have the same characteristic, and then you can market your product to them differently with different strategy, right? So that's the purpose of unsupervised learning or clustering. And today we are going to walk over a case. It's the same type of data. For example, this is a data set. It's an ideal data set. Okay, not a real data set. Right? It only has a few cases. So we assume that it's going to be height and weight, and with a few cases. So how do we group them? Okay, if you observe, we human beings can easily observe this. These could be a good group, and these can be a good group. But how do the computer classify them, group them? We said that it will start with some randomly picked up centroid, like a center. We pick up some random center. For example, I pick up this as a random center. And this as a random center. Then how does it classify each dot? It calculates the distance. For example, this dot, should it be group 1 or group 2? It calculates the distance. If this distance is smaller here and larger here, then this goes to the group 1 instead of the cluster group 2. So that's how it classifies all the dots into the 2 groups. If we define this, if you wanted to classify into 2 groups, okay, to put into 2 groups. So, so these centroids, they are randomly picked up, and these centroids are randomly picked up. It cannot. It could be not the ideal ones. It could be not the ideal ones. Now, how do they find the ideal centroid? After it's grouped, after it's grouped, hey, these are all These are all classified as the second group, or these are all classified as the first group. And then if you calculate the mean of this group, for example, the mean, it could be somewhere around here. This mean could be somewhere around here. And then it calculates the distance again and to see if we need to be changed. Sometimes that it has to be changed. Give another example. Give another example, okay? The randomly picked up centroid, the first centroid, it was here, okay? So it was here, the second one, it was here, the third one, this two. And then at the beginning, these might be classified as group 1, and these might be classified as group 2. Group 2. Oh, now we calculate the mean of these centroid, okay? The mean of these two groups. The mean of these two groups is the first one maybe here, and the second one is most of the dots are here. So it would go over this way. The mean, the centroid of the second group, it will be changed to here. Why? All the dots are here. All the red dots of the second group are here. Does it make sense? So the first two are randomly picked, and then they assign the distance to classify these dots. And now it formed two groups. This is the first group, and this is the second group. And then it tried to find the center of cluster 1 and cluster 2. Center of cluster 1, because the two dots here, the center may be close to the original one. But the center of the cluster 2, because most dots are over here, over this corner, the center of this cluster will be moved to this side. Does it make sense now? Yeah, it will move this side. And then after the center moved here, it will reclassify. It will do the classification again. It will do the classification again with the center. Calculate each distance. Okay, these dots are probably, these dots, like this dots, it was in group 2. And now from these two new center, it looks it's closer to this group 1. So it will be corrected to group 1. Will be corrected to group 1. And these will be corrected to group 1 as well. And this one, it was in group 1. It will be corrected to group 2. And it will, so now it changed to this is group 1. And these will be group 2. And then it find the center again, and to see if these need to be corrected. So it will continue to correct until the center doesn't move again, then they find the ideal center. Okay, that's how the algorithm works. So actually, in the last lesson, I mentioned that how it works is the first, it picked up 2 random dots, like I said today. It picked up 2 random dots. random centroid, and then it classify. Okay, this looks good. Two groups, and then randomly pick up 2 other dots. This is the first cluster method. Okay, the first one. And then if you randomly pick up 2 other dots, 2 other dots here, 2 other dots, 2 other dots here, and then form two cluster also. How you find the ideal cluster? How you find the ideal cluster? It calculates the variation. For example, the variation of all the dots to this dots to the centroid, to the center. Okay, the center of the cluster is this distance, and this all the dots, the distance to this center is adding all these distance together. Of course, it has negative and positive. It should have used a square number, squared number. So that forms the second center. And how it compare the first center and the second center, it calculates all these distance and add all these distance together. And if the clustering is good enough, this distance should be small, right? And compared to the first one we did, the first one we did is this group, and these distances are very large. The first method, the distance, the dots are the points are very apart from each other. The first method, the variance is larger than the second one. So the second one wins. And randomly pick up all these, each randomly pick up 2 until you find the smallest variance. So the problem with this one is that if you randomly pick up 2, every time you randomly pick up 2, here, and for example, I have 10 total dots. How many times it takes to pick up 2? How many times it has? It has 10 dots, and it has a pick up 2. If you take how many times? It's 10 times 9 divided by 2, I believe, right? So we have to repeat this 45 times. It's not efficient. It won't be efficient. So, and after read some other materials, I found no, this the first source I referred to is not correct. Instead, what it does is to randomly pick up, and then it correct it, randomly pick up 2 group, and then it collected the center. The center should be here, and then it recorrect these dots to the correct group until the center doesn't move anymore. So there are different explanations for the algorithm, and oftentimes you find that one resource is wrong, and well, one resource looks correct. Okay, the variance, you randomly pick up the dots, and then you find that the method with the smallest variance. That means that the dots are close together. It sounds very correct. I thought this again last night. Okay, now the efficiency, it takes these 10 times 9 divided by 2, 45 times to repeat this process. That doesn't sound right. And when I go over more materials and find, okay, yeah, it was wrong. Oh, why it didn't apply to the one direction, one dimension data here? I couldn't explain. I still couldn't explain. Yes, on Monday I used this case, one dimension. So I randomly pick up the dots here. The first as a centroid, second as a centroid, and then the third one as a centroid. This one as a centroid, and then these will be classified as one group. These will be classified as one group, and all these will go to the third group. And then it find means using the method we talked about today. You find the centroid again, the new centroid. I find the new centroid, the mean of each centroid. So these are the original centroid I randomly picked up. And then it's find the centroid. After it grouped, I find the centroid of the group. And then it will correct all these dots to the nearest mean, right? So these still goes to here. These still goes to here. These still go to here, and all these should still go to there. Probably this will. All these should still go to this cluster, and then all these still go to this cluster. It didn't change. It didn't change the mean. So it will stop here. But this one, obviously, it's not the best cluster because by observation we find that these might a good group. This is a good group. This is a good group. So it doesn't explain in this case. My only explanation is that this data is too delicate. This one, after reclassifying, correct it, this one may go to the side instead. So it will correct also, but it will be moved and then it will regroup and until it finds these as these as the cluster, and this should be the cluster. But the correct way of explaining the algorithm is not to pick up randomly pick up 2 dots and then pick up 2 dots again until you find the smallest variance. So instead, it's correct according to the with the centroid. The correct with the centroid. Until you find the best centroid and it doesn't move at all. So yeah, it's very interesting to study this algorithm, and then sometimes you get confused, and then you have to keep exploring and to see which one is correct. Okay, so come back to this Okay, come back to this. What we need to group, what we need to cluster this is just like we did with the logistic regression or other method. You just use the method. You just import this method and then use this algorithm. Okay, this could be KM, and this let's fit use the data to train this model. And here the only difference is we used to have a y as the target variable. Here you don't have y anymore, only x. And the x should be the 2 column you had. We had you could use rock. Get these 2 columns. Yeah, actually, the entire data set is just use the entire data set. There's no other variable, so it's just then I generate the algorithm, and then with this algorithm, you can use it to predict. If there's a new dot, you can use it to predict the new dots. So let's get a view of the algorithm first, okay? Or the result first. So we trained this algorithm, and then we can use this algorithm to predict, to know, hey, what is the result? The result is use it to predict the original data, and then it will get the labels of what you call result, whatever labels for each dot. Get the labels of each dot, and also we can get the centroid. The centroid is I believe it's a K cluster center. And it should give you, since we're here, we defined the 3 cluster. We want to classify into 3 clusters, so it should give us 3 3 dots with XY. Cluster centers, okay. So this is the X, this is the Y, and then there's 3 centroid, okay. Now we can use this data to label it. For example, plot these centroid on the picture, and also use colors to label these dots. So what I did is to define a color. The color could be red to represent the first group, and the blue to represent the second group. Green to represent the third group. And for each label, so these are the labels for each dot, right? So for each label, if it is 1 for I in labels, if I is 1, okay, you use the first one. You use the, if I is 1, I iterate through this list. If I is 1, okay, it gets the red color, and if I is 2, it gets the blue color. Likewise, right? So it's a for loop, and then the color you get is the CI. CI is the color you get. So for example, I is 1, okay, the CI is the red. I is 2, then this, I is 0, it gets the red, and I is 1, it gets blue color. So that's the CI for matching to each case, matching to each case, and we needed to use another list to store this. So this. If we print out this list, how it should look like. So we print out this color, this list, how it should look like. I transformed this one to the colors, the red, green, right? It should be a RRR, BBB, GGG. Oh, where are we confused here? Oh, okay. And now we can plot this again, plot the scatter plot again, but the color is not just a red. Apply this. Yeah, but the color should not be the red. The color should be this list. It goes over this list, so it should be colors. Size is still 18 or whatever size it prefers. That's it. That's the size of the dots, and also we can plot the centroid. The centroid. It's a 2D array, so the X should be the first column. Our first column is 0, and the Y should be the second column. Color C equals, I just use red again. Maybe I can use yellow. I use a bigger size. So this shows the result of the 3 cluster, the best 3 cluster, and with its centroid. Okay. I want to insert a question. So with this case, do you think this k-means, for this k-means algorithm, do we need to scale the data or not? I didn't scale the data. This one, it's 8 and it's 9. It's pretty much the same range. If it's on a different range, do we need to scale the data? Scaling, normalize, or standardize. Yeah, because it uses the distance, right? It calculates the distance. You don't want one feature on the side to dominate the distance. Same as similar to k nearest neighbor we learned. So if this range is 1 to 100, the numbers of x is 1, like 10, 100 or 200, and this one, the numbers for this side is 1, 2, 3, 4. So x will dominate the value, the distance. Y will have a little influence on the result. So we don't want this to happen. I just scale the data. Okay. So by this, when looking at the picture, you might be wondering, okay, it doesn't look like, I don't like this result. I feel 2 groups must be better, right? Better than 3 groups. So how do we find the optimal K? How do we find the optimal K? So we said that we calculate the distance, the variance, all the variance, like we said at the beginning, it calculated the variance of the cluster. Okay, add these variances together and add these variances together. For cluster 3, okay, this is maybe like this is a various as a number, a variance 1. Okay, variance 1 might be the 3. Okay, variance 3 is all the variances together for these 3 clusters. And then when you have more clusters, does this variance go down? Yeah, for example, it goes to 10 clusters. All the dots form a cluster. Then the variance is each cluster, the variance is 0, and all the variance together is 0, right? So does that mean, hey, that's the best cluster? No, not. So what this algorithm does is, as the K increase, the sum of variance, or the official name is the sum of squared error. Sum of the squared error. This goes down. But at some point, it doesn't go down very quick. If you form a picture like this, it goes down from 1 to 2, okay, and then later it will slow down, and this is the apple point, the optimal K we want to find. So with this, we know how to iterate this. Like the K nearest neighbor we use, okay, you get the 4 K from maybe 1 to 10, and then you get the sum of squared error for each algorithm, and then you find the best algorithm, the best K, right? So what it does is we iterate this K for K, range 1 to 10, and then we repeat how we copy this, right? we copy this, and then the cluster number of cluster goes from 1 to 10. And then the value we need to get is called inertia. That's value we need to get, and then we save it to a list. We name it as SE, okay? And we get the sum of squared error for each algorithm, and then we save it to this list. And if we print it out, how it will look like, how this list will look like, it goes down as the number of clusters increase. There might be some spelling error. Oh. Goes down from 258 to 5. Of course, if we change this to how many together, 15, or it should go to 0. It should almost go to 0. Yeah, but this is 15. Yes, that's it. 4, 7, 10. Yeah, it goes to almost to 0. Right? If it's the same number, it should go to 0. And where is the optimal K? Is that as it decreases at some point, it doesn't decrease as fast as it was, and that is the optimal K you want. So we need to plot this list, plot out this number. Oh, plot, and the x should be the K number from 1 to 14. Oh, no, that's an X. Should be K number from 1 to 14. And then the Y should be this list. I guess that's it. Look at this data. Look like an apple. And where it's turned, it's slow. Number 2. So that's an optimal case. We want. Okay, in this picture, it's very easy to identify this apple point. That it turned slow. The slope potential is slow. In some cases, it's not that obvious. So you can use this code to let the computer calculate the apple, find the apple for you. Okay. That's a method we need to know. However, there's another method, metrics, to find the optimal K. They're called Sihu coefficient. What it does is similar to this apple method, but a little bit different is it doesn't just calculate the coherence. It doesn't just calculate the cohesive, right, whether these dots are together or not, but also calculate whether the dots are apart, are far away from the other cluster or not. For example, this 3 group, these dots are not that far away from the other group, then it's not the ideal cluster. So the formula for this is 1 minus A. A is the distance, the variance, the sum of variance we said, right? The sum of each dot to its centroid. So let's measure whether these dots are together or not. The better, the more together they are, the better the cluster, right? So A measures whether the dots are together or not. And of course, it could be a lot of dots and it could be a few dots. So you should get the average. So A is the average distance of all these dots, the variance of all these dots to the centroid. And also it calculated the dots, whether this is apart from the other dots or not. So it calculated this distance to the nearest cluster. Maybe this one, maybe this one. It calculated both, and then get its distance to the nearest cluster. That's a B, and the average distance. The average distance to the all the other dots in this cluster. Okay, so this one, and it calculates minus. So this one, the A is larger. A is larger. This number should be, no, A is smaller the better, right? We want this to be together. So A is the smaller the better, and it has a minus, so because the larger, in reverse to this. And the B, the farther distance, then this is better. So that's the method how this CQ coefficient works. And this is a case that walk you through this. For example, you calculate the dots, calculate the coefficient of the dots, then you have to average all these distance to A, and then average all these distance, this distance to B, and then you get the result. But generally, the idea is the closer the variance of this is smaller, and the variance of this is larger, the better. Part the better. Okay, how do we get this with the code? That's pretty the same, but has another, need to import this matrix instead. Import this distance metric, and you can reuse this code. K means fix K, and this is not inertia, but it's another metric. So this is called a matrix CQ score. Okay, CQ score. That's the one you need to get. And for each score, so you like we did, we append it to a list, save it to a list. And it should give us it should have given us a list that this number goes up because this is reversed. See, this is reversed. So as the k increase, this variance, this internal variance will go down, and this is the final CQ matrix. So as the k increase, then this internal variance is go down, and this will be it goes down. So and it has a minus, so this will goes up, and the B if it has a more, B should be, because if it has more clusters, and then the average distance, so the B, if it has more clusters, then the B should its distance to other clusters. So it used to be far away, and then it has more cluster. For example, these two could be the cluster close to it, and then this B should goes down also. So, but it's on the denominator, so this one also goes up. So the CQ score will goes up as the k increase. I printed it out. Should be the correct one. Oh, yeah. This look correct. Okay. No, I use this name here instead. So this should be correct. Valid values are 2, 2, and okay. So it doesn't allow, believe it doesn't allow 1 here. Only start with 2. It doesn't allow 1, number 1 here. That's why it was wrong. Yeah, if it's number 1, it doesn't have the other cluster to calculate the distant to the other cluster. Does that make sense? Yeah. You start there also? Okay, let's fix that. So because with this method, it calculates its distance to the other cluster, and we use the number one. If it has only one cluster, it doesn't cannot calculate its distance to the other cluster. That's why it doesn't allow number one here. You have to start with number two. Okay, and so the first one is the best cluster because it has the largest CQ score. Right. With this result, said the last step is to interpret, understand how they cluster it. So the computer, the algorithm give us the result, a two cluster is the best. And then we have to understand how it clusters. For example, here, it's obviously it classified a X is smaller, it comes to the first cluster. And then if the X is larger, then it goes to the second cluster, right? So usually you pick up the but the y-axis also explained. Y-axis also explained because these are like y is smaller, then it goes to the first cluster. But it's not as good as the x, y. Some of this has overlap over the same area, right? It's not completely distinguished. So X might be the better feature to explain how it clusters. So for example, if it has multiple features, a data set with multiple features, we can, now we have the labels. Now we have the labels. So you can find the feature that with the gives you the most significant variance using the ANOVA test to find it, and then use that to explain the result. Okay, the last one is the dimensionality reduction for clustering or supervised learning. So now with the if it has multiple dimensions, then the efficiency of the algorithm decreases significantly. And so in previous lessons, we learned using ANOVA, using the chi-squared test to remove those unrelevant variables, all correlation to find the highly correlated column. But here, in this case, it will not work because it doesn't have a target variable, right? So how can we reduce the dimension for clustering? This is the most popular ways to reduce the clustering. Principal component analysis. So it combines the variables into fewer variables. What it does is to use the linear relationship between the variables. For example, and multiple dots here. Okay, we use x, y. There are two variables right now, x1, x2, or x1. They are related, you see. Oh, not good to change it a little bit, okay. These are two variables, x1, x2. Which one is the better, is a better feature? The one with the most variance is a better feature. Because this x2, it goes to the extreme, and extreme example, the x2, the y, this dimension, all the data has small, very small variance. All they're uniform. We don't want this feature, right? So we want to find the feature that has the best variance. The more variance it has, the better variance it has, it's a better feature. Right? And this the principal components analysis, what it does is, okay, x2, x1 has a relationship. I want to maximize the variance. That is this dimension. This dimension, it should be a straight line. This dimension, it captures the best variance of both the x1, x2. So instead of using these numbers, I use these distance to capture both the distance, the variance of x2 and the x1, and then merge these two variables into one. A little bit hard to understand, but that's a basic idea. It changes the dimension and find the maximize the variance of this variable. And then the second principal component, it goes this direction, 90 degrees with this first one to capture the variance. So in that, if we don't use this one, you don't use the second one, use the first principal component, and just reduce from 2 dimensions to 1. So that's how it reduce the dimensions. Okay, that's a basic idea behind the principal component analysis. There are some tutorial, a lot of tutorials explaining that. You can further explore. And also we can use our domain knowledge to make the decision to remove the dimensions. For example, this is a very good case, shows you how reduce the dimension. It's a data set about retail. Original data has an invoice, unit price, customers. So I want to identify the customers, merge all the combine the data by the customer ID. So we got how many purchases they made, and the recent date they purchased. That is the frequency they purchased. The frequency they come to shop here. So toward the end, I reduced it to only three variables. One is the amount, the total amount they purchased, and then the frequency, how many times they purchased, and then the most recent purchase, whether they just purchased yesterday or they purchased long ago. Then these may not be good customers, they may already be gone. So this is a good case to study about how to reduce the dimension also with your domain knowledge about the data set. Okay, and the first one is the example of reduce the dimensionality by with the principal component analysis. These are two common ways to apply feature reduction for unsupervised learning. Okay. Okay, that concludes our lesson today, and then next, and then we can answer some questions and look into the assignment. I mentioned to the class who was here on Monday. So Mihong, he has a broken bone, and he has a surgery scheduled next week. Maybe he needs some help in the recent weeks, at least some 1 month or 2 months. Has a surgery next week, and then after that he can not get on the floor for a couple of weeks. If you can help for meals or anything, you just email him and say if he help you. Okay.